Good day everyone and welcome to our presentation.
Today we delve into the fascinating world of neural language models with our research titled Scaling Laws for Neural Language Models. We explore the intricate dependencies of language modeling performance on various factors, and our findings suggest that larger models could be the key to better performance and efficiency. So let's embark on this journey to uncover the hidden potential of neural language models.
Stay tuned.
Our study aims to understand the dependence of language modeling performance on various factors. We focus on the transformer architecture, given its high potential for performance on language tasks.
We build upon existing models that have achieved human-level performance, with the goal of further understanding how language modeling loss depends on different factors.
In our research methodology, we trained a variety of models, adjusting factors such as model size, dataset size, shape, context length, and batch size.
The datasets we used were extensive, ranging from 22 million to a staggering 23 billion tokens.
This comprehensive approach allows us to observe precise power law scalings for performance as a function of training time, context length, dataset size, model size, and compute budget. In essence, our research is a deep dive into the world of language modeling, aiming to unravel the intricate dependencies that govern its performance. We believe that our findings will pave the way for more efficient and effective language models in the future. Our research has led to some key findings. We've observed consistent scalings of language model log likelihood loss with non-embedding parameter count, dataset size, and optimized training computation.
Interestingly, we found a very weak dependence on many architectural and optimization hyperparameters.
This study goes beyond just observations. It provides a predictive framework for understanding loss dependence on various parameters.
This has significant implications for the future.
Our results suggest that larger models will continue to perform better and be more sample efficient.
Furthermore, we believe that model parallelism could be a game changer.
It may allow for faster training of large networks, opening up new possibilities in the field of artificial intelligence. This is an exciting time for AI research, and we look forward to seeing how these findings will shape the future of language modeling. Language serves as a rich domain for AI research, offering a wealth of data for unsupervised learning through generative modeling. Our aim is to understand how language modeling performance is influenced by various factors.
The figure you see here illustrates the power law relationship between model size, dataset size, and compute used for training.
It underscores the importance of scaling up all three factors in harmony for optimal results. This understanding will guide us in our quest to develop more efficient and effective language models. We're diving into the world of transformer architecture, a domain with a high ceiling and low floor for performance on language tasks.
Recent advancements have brought us closer to human-level performance on various tasks, a truly exciting development. However, despite these strides, we still need a deeper understanding of how different factors impact performance.
Our study aims to shed light on this.
We're conducting an empirical investigation into how language modeling loss depends on a variety of factors.
These include the size of the model, the size of the dataset, the shape of the model, the length of the context, and the batch size. By understanding these dependencies, we can better optimize our models and push the boundaries of what's possible in language modeling. This is a journey of discovery, and we're excited to share our findings with you.
In our research, we've identified key scaling factors for optimal performance in transformer language models.
To achieve the best results, it's crucial to scale up all factors, model size, data size, and compute used for training simultaneously. Interestingly, we found that performance follows a power law relationship with each of these factors, provided they're not being limited by the others. Now let's talk about performance penalties. These penalties are predictable and depend on the ratio n to the power of 0.74 over d. In practical terms, this means that if we want to increase the model size by a factor of 8, we need to increase the data by roughly 5 times to avoid a performance penalty.
This insight can guide us in efficiently scaling our models without incurring unnecessary costs or performance drops.
Our research zeroes in on the transformer architecture, aiming to unravel how language modeling performance is influenced by various factors.
We've trained a wide array of models, with datasets ranging from 22 million to a staggering 23 billion tokens.
Diving deeper into our methodology, we've trained models of different sizes and experimented with varying context lengths and batch sizes. This approach has allowed us to empirically investigate the dependence of language modeling loss on these factors. But what sets our research apart? We've developed a predictive framework that allows us to understand this loss dependence. This unique approach has given us valuable insights into the intricate workings of language modeling.
We believe these findings will pave the way for more efficient and effective language models in the future.
Our research delves into the experimental design and improved aspects of language modeling.
We evaluated performance based on log likelihood loss, observing consistent scalings of loss with non-embedding parameter count, dataset size, and optimized training computation.
Interestingly, we found a weak dependence on many architectural and optimization hyperparameters. This leads us to predict that larger models will perform better and be more sample efficient. But this raises key questions. How do different factors impact language modeling performance? And do smooth improvements in language model loss hide qualitative changes in capability? These are the questions that guide our research and shape our understanding of language modeling. Our research has led to some key technical results. We found that the log likelihood loss in language models scales consistently with non-embedding parameter count, dataset size, and optimized training computation. Interestingly, many architectural and optimization hyperparameters showed only a weak dependence.
As we scale up, we do see diminishing returns, but there's a silver lining.
We've observed a smooth improvement in language modeling performance as we increase model size, dataset size, and the compute used for training.
However, to achieve optimal performance, it's crucial to scale up all three factors together. When we're not bottlenecked by any of these factors, empirical performance shows a power law relationship with each one.
This suggests that larger models, larger datasets, and more compute power can lead to better performance, but they need to be balanced for the best results. Our research findings have significant implications.
Firstly, we found that larger models not only perform better, but they are also more sample efficient. This means they can achieve the same level of performance with fewer optimization steps and using fewer data points.
Secondly, we've developed a predictive framework that allows us to understand how the loss depends on various parameters. This is a crucial step in optimizing the performance of our models. Thirdly, we've identified that model parallelism, which is the process of training large networks faster, is an area that warrants further investigation.
Lastly, we've discovered a predictable performance penalty based on the ratio n0.74d.
This implies that for every 8x increase in model size, we need to increase the data by roughly 5x to avoid a performance penalty.
This insight is invaluable in guiding the scaling of our models. In summary, our research provides a roadmap for the development of more efficient and effective language models.
In conclusion, our research provides a comprehensive understanding of the factors that impact language modeling performance. We've conducted an empirical investigation into how language modeling loss depends on these factors, with a particular focus on the transformer architecture. We've trained a variety of models, varying factors such as model size, dataset size, shape, context length, and batch size. We then evaluated their performance based on log likelihood loss. Our findings reveal precise power law scalings for performance as a function of these factors. This work not only contributes to our understanding of language modeling, but also provides a foundation for future research in this field. We believe that, as we continue to scale up model size, data, and compute, we can expect larger language models to perform better and be more sample efficient.
Thank you.
Our research has led us to some key takeaways. We've found that the log likelihood loss in language models consistently scales with non-embedding parameter count, dataset size, and optimized training computation. Interestingly, many architectural and optimization hyperparameters show a weak dependence.
We've also discovered that larger models not only perform better, but they are also more sample efficient.
This suggests that the future of language modeling may lie in larger networks, and model parallelism could be a promising approach for faster training of these large networks.
Our work has also resulted in a predictive framework that helps us understand the dependence of the loss on various parameters. This is a significant step forward in our ability to predict and control the performance of language models.
Furthermore, we've observed that continued improvement on the loss may translate into improvement on relevant language tasks.
This is an exciting prospect, as it suggests that, as we continue to refine our models, we can expect to see real-world benefits.
Finally, we've noticed that smooth improvements in language model loss may hide seemingly qualitative changes in capability.
This is a reminder that even small improvements can lead to significant changes in the capabilities of our models.
In conclusion, our research has provided valuable insights into the scaling of language models and has opened up exciting new avenues for future exploration.